In the final years of the 19th century, the world seemed to have unlocked nearly all the great mysteries of nature. The laws of Isaac Newton described the motion of the planets and the fall of an apple with the same precision. The theories of James Clerk Maxwell had united electricity and magnetism into a single elegant framework that predicted how light travels through space. It was a golden age for science, a time of confidence, reason, and triumph. Many physicists believed that the grand structure of knowledge was nearly complete, that only a few minor details remained to be filled in. Yet, hidden within the glow of lamps and the heat of furnaces, something strange was happening, something that did not fit into the perfect order of classical physics. It was a mystery buried in the very nature of light and matter, waiting for the one mind daring enough to see beyond the limits of established truth. In those days, light was thought to be fully understood. It was a wave, a vibration of electromagnetic fields spreading across the universe. The equations of Maxwell had confirmed this beyond doubt, showing that light waves moved at a constant speed, forming the bridge between electricity, magnetism, and optics. Experiments had proven that light could reflect, refract, and interfere exactly like water waves. The scientists of Europe, proud of their triumphs, believed there was nothing left to question. Yet, as the century approached its end, one persistent puzzle haunted laboratories across the continent: the way objects emitted light when they were heated. Every blacksmith, every potter, every engineer had seen the phenomenon countless times. As an iron rod was heated, it began to glow, first a dull red, then bright orange, and finally white hot. The color of the glow changed with temperature, and so did its brightness. Scientists tried to measure this relationship precisely, to find a formula that could describe how much light of each color was emitted by an object at a given temperature. It seemed a simple task, but the deeper they looked, the more the problem defied them. The challenge was known as blackbody radiation, the emission of energy from an idealized object that absorbs and emits all radiation perfectly. In experiments, physicists built hollow cavities with tiny holes to approximate a perfect emitter. When heated, these cavities produced a continuous spectrum of light, radiation at every wavelength, but the intensity of each wavelength changed in a peculiar way. The problem was not with the measurements, it was with the theory. According to classical physics, the amount of radiation emitted should increase infinitely at shorter wavelengths. The equations suggested that as you moved toward the ultraviolet region, the energy output would explode to infinity. Yet reality told a very different story. The intensity dropped smoothly to zero. The theories were wrong, and no one could explain why. This contradiction became known as the ultraviolet catastrophe, and it struck at the heart of physics itself. It was not a mere calculation error. It meant that the very foundations of science could not explain something as ordinary as the color of hot metal or the warmth of sunlight. Every attempt to fix the equations failed. Physicists like Lord Rayleigh and Sir James Jeans tried to adjust the classical formulas, but their predictions still blew up in the ultraviolet range. The data and the theory simply refused to match. Nature was whispering a secret, one that the existing laws could not hear. Meanwhile, other experiments deepened the mystery. In laboratories across Europe, scientists studied light as both wave and energy. They had discovered diffraction, interference, and polarization, all proofs of light's wave, like nature. But certain phenomena, such as the way metals emitted electrons when exposed to light, hinted that light might behave as if it were made of particles. But at the time, no one dared question the wave theory. To suggest that light might also have a particle nature seemed to drag physics backward, not forward. The idea was unthinkable in a world that prized mathematical beauty and continuous motion. Still, the evidence lingered, unresolved and ignored. At the same time, the nature of matter was equally mysterious. Atoms were believed to be indivisible building blocks, tiny solid spheres obeying Newton's laws. But those laws could not explain the strange patterns seen in the spectra of gases when heated or electrified. Each element emitted light at specific colors, unique fingerprints of their internal structure, but the cause remained unknown. No one could understand why atoms emitted energy in such distinct patterns, or how electrons behaved within them. The universe, which once seemed a predictable machine, was beginning to look far more complex and far more mysterious. The 1890s were thus a decade of quiet confusion for physicists. They were armed with the most elegant equations ever written. Yet they could not explain the simplest natural behaviors of heat and light. This paradox was more than an academic frustration. It was a signal of a deep flaw in the framework of science. Somewhere, hidden within the equations of classical mechanics and electromagnetism, lay a missing piece. But no one knew where to look. The great names of the era, Kelvin, Boltzmann, Wien, each took their turn, offering theories that worked for some ranges of temperature or wavelength, but failed for others. The data refused to fit neatly into any formula. One man, however, refused to ignore the problem. His name was Max Planck, a German physicist and professor at the University of Berlin. Planck was not known for radical ideas. He was a careful thinker, deeply devoted to the laws of thermodynamics and the belief that nature's order was absolute. He sought harmony in mathematics and beauty in truth. When he turned his attention to the problem of blackbody radiation, it was not because he wished to overthrow physics, but because he believed it could be solved within the existing framework. In his mind, the laws of energy were perfect and unbreakable. He could not imagine that nature would defy them. Planck began by studying the work of Wilhelm Wien, who had developed an empirical law describing how the intensity of radiation varied with wavelength and temperature. Wien's formula fit the experimental data at high frequencies, but failed at low ones. Planck sought to refine it using the principles of entropy and thermodynamics. He worked tirelessly, experimenting with mathematical models, adjusting constants, and searching for a formula that matched the observed curve of radiation. For a time, it seemed impossible. The data were stubborn, the mathematics merciless. Then, on an October evening in 1900, after weeks of relentless thought, Planck found a path forward, but it led him into forbidden territory. To make his equations fit the data, he had to assume something entirely new. That energy was not emitted continuously, but in discrete packets. In other words, atoms could release or absorb energy only in specific amounts, not in an unbroken flow. He called these packets quanta. At first, Planck considered this nothing more than a mathematical trick, a convenient assumption to make the equations work. But beneath that assumption lay a deeper truth, one that would change the world. In Planck's model, the energy of each quantum depended on the frequency of the radiation, the mole, where was a constant he introduced to make the numbers align. This Planck constant would soon become one of the cornerstones of all physics, defining the scale of quantum effects in the universe. By quantizing energy, Planck not only solved the blackbody problem, but also revealed that nature itself might be discrete at its most fundamental level. Light and matter, once thought continuous, were now bound by the mysterious rhythm of quantization. Yet Planck himself was uneasy. He did not believe his discovery represented physical reality. To him, it was merely a mathematical device, a temporary patch. He even wrote that he had acted against his own convictions to derive the formula. He could not yet imagine that his reluctant idea had opened the door to an entirely new world, the quantum world. But the cracks had formed, and the wall of classical certainty was beginning to crumble. Meanwhile, outside Planck's study, the scientific world was on the verge of transformation. Within a few short years, Einstein would seize upon Planck's quanta to explain the photoelectric effect, proving that light itself could act like a stream of particles. Bohr would use quantization to describe the structure of the atom. Heisenberg and Schrödinger would later build the full framework of quantum mechanics. But none of this was visible yet. In 1900, there was only one man standing quietly before his blackboard, holding a piece of chalk and a radical thought. He did not yet fully understand the early mystery of light and matter was not just a puzzle of numbers and formulas. It was a turning point in human understanding. For centuries, humanity had gazed at the stars and the glow of fire, seeing only beauty and warmth, but behind that glow lay a code, a pattern written in the language of quanta. Nature was whispering a secret through the color of heated metal, through the faint shimmer of light. And Max Planck, guided by logic and curiosity, became the first to listen. In that moment, physics stepped into its own twilight, caught between the fading light of classical certainty and the first flicker of the quantum dawn. The story of light and matter had begun anew, not as a tale of waves and particles alone, but as the story of humanity's greatest intellectual adventure, the journey into the quantum world. The story of light and matter did not end with Planck's equation. It had only just begun. Though the world celebrated his mathematical triumph, very few realized that a revolution had quietly taken root beneath the calm surface of physics. To most scientists of the time, Planck's discovery was a clever trick, not a revelation. They applauded the accuracy of his formula, but ignored the depth of its meaning. The idea that energy came in indivisible packets went against every instinct of classical science. Energy, like matter, was supposed to be continuous, measurable in infinitely small portions. The suggestion that it could come in jumps, like steps on a staircase rather than a smooth slope, felt absurd. Yet the universe, as it turned out, was far more subtle than human reason had assumed. For centuries, the notion of continuity had been the guiding light of physics. From the orbits of planets to the ripples on a pond, everything appeared to move in an unbroken flow. The mathematics of calculus, the pride of Newton, was built upon this very idea, that change occurs smoothly, infinitely divisible. To question continuity was to challenge the very soul of physics, but nature does not care for human comfort. Planck's quanta whispered a truth that reason had long ignored. Reality, at its deepest level, is granular. The first hints of this strange new world appeared not in grand discoveries, but in small inconsistencies, like cracks in an old painting. Light, the most familiar phenomenon of all, refused to behave properly. Sometimes it acted like a wave, spreading, bending, and interfering. But in other experiments, it behaved like a stream of particles, knocking electrons out of metals, as if it were a hail of bullets. The dual personality of light puzzled everyone. If it was a wave, how could it eject electrons? And if it was a particle, how could it produce interference patterns? Classical theories could not reconcile the contradiction. The mystery of light deepened, and Planck's reluctant idea began to look more real. It was Albert Einstein who took the next daring step. In 1905, he proposed that light itself was quantized, that it consisted of discrete packets of energy, later called photons. Using Planck's constant, he explained the photoelectric effect, showing that only light of a certain frequency could liberate electrons from metal surfaces. It was a direct confirmation that energy was not continuous but came in bursts, proportional to the frequency of light. The implications were staggering. Einstein had transformed Planck's mathematical convenience into physical truth. The quanta were real, but Einstein's insight did more than explain one experiment. It suggested that the very fabric of the universe was built upon quantum principles. The world of light, once thought to be a smooth wave spreading endlessly through space, was in fact a dance of energy packets. Tiny, indivisible, and mysterious, the discovery shook physics to its core. It meant that light and matter were not entirely separate entities, but two sides of the same coin. It meant that nature operated by rules that no one had ever imagined. Still, the full significance of this discovery would take decades to unfold. In those early years, physicists struggled to accept the strange implications. Even Planck himself resisted Einstein's interpretation, unwilling to believe that light could truly be quantized. The idea seemed too radical, too disruptive. Yet, as experiments multiplied, the evidence became impossible to ignore. Each new study of atomic spectra, of radiation, of heat and electricity, confirmed the same hidden truth. The universe was built not from smooth flows, but from discrete steps. Meanwhile, another question emerged. If light could behave as both a wave and a particle, could matter do the same? The boundary between energy and substance began to blur. The old certainty that atoms were solid, indivisible spheres crumbled as new experiments revealed the complexity within. Electrons, protons, and neutrons, each seemed to follow rules far stranger than Newton ever imagined. When scientists tried to track the motion of these particles, they found only probabilities, not certainties. The more closely one looked, the less defined things became. The early mystery of light and matter thus evolved into a deeper paradox, one that lay at the heart of all existence. How could something be both continuous and discrete, both particle and wave? The answers would come later, through the work of Bohr, Heisenberg, and Schrödinger, but the seed had already been planted in the glow of Planck's blackbody. That simple study of heat and light had unknowingly opened a portal into a world where logic bends and intuition fails. As the years passed, laboratories around the world became theaters of discovery. Spectroscopes revealed the hidden fingerprints of elements, showing that each atom emitted light at specific wavelengths. These lines, once mysterious, began to make sense under the new quantum framework. The electron, circling the nucleus, could exist only in certain energy levels. When it jumped from one level to another, it emitted or absorbed a quantum of light. The colors seen in the glow of gas lamps, in the auroras of the night sky, and even in the starlight from distant galaxies, all were signatures of quantum transitions, of tiny jumps of energy governed by Planck's constant. The revelation was both humbling and awe-inspiring. Humanity had long sought to understand the universe by observing the grand and the vast, the motion of planets, the pull of gravity, the rhythm of tides. But the true secrets of nature lay in the smallest scales, in the invisible dance of particles and waves that make up everything. It was a realization that turned philosophy itself upside down. Reality, once thought to be solid and continuous, was built from probabilities, vibrations, and energy quanta. The universe was not a machine, it was a symphony of uncertainty. Planck, in his quiet way, watched this transformation unfold with a mixture of pride and disbelief. He had never set out to start a revolution. He was a conservative physicist, grounded in the traditions of determinism. Yet the laws of nature had chosen him to be their messenger. The more the quantum theory evolved, the more it departed from the world he had known. It spoke of randomness, of chance, of limits to knowledge. It told of particles that could be in two places at once, and of energies that existed only in discrete steps. For Planck, it was both a triumph and a mystery. He had opened the door, but others would have to explore what lay beyond it. As the 20th century progressed, the influence of Planck's discovery spread far beyond physics. Quantum theory began to reshape chemistry, biology, and even philosophy. It revealed that atoms could bond, not by physical contact, but through shared clouds of probability. It showed that energy and matter were interchangeable, that time and space could stretch and bend, and that observation itself played a role in shaping reality. The once simple question, how does a hot object emit light, had led to the most profound redefinition of existence ever conceived. In retrospect, the early mystery of light and matter was not a failure of classical science, but its natural evolution. The old theories had brought humanity far, describing the visible world with astonishing accuracy. But they could not see the invisible, the microscopic realm where energy moves in leaps and matter dissolves into waves. Planck's discovery bridged that gap. It was as if a curtain had lifted, revealing a hidden layer of truth beneath the surface of reality. The power of this revelation can be felt in every corner of modern life. The screens that glow with digital light, the semiconductors that drive computers, the lasers that perform surgery and carry information through fiber optics, all owe their existence to the understanding that energy is quantized. The world that once puzzled Planck in his Berlin laboratory has become the foundation of the technologies that shape our daily lives. Yet, even now, the mystery remains. Quantum physics, despite its success, continues to challenge intuition. Its predictions work flawlessly, but its meaning eludes comprehension. And perhaps that is the beauty of it. For every answer, it offers a deeper question. What truly is light? What is matter? Are they separate? Or are they merely different expressions of the same underlying reality? The journey, that began with Planck's study of glowing metal, has become a philosophical quest as much as a scientific one. It asks not only how the universe works, but what it means to exist within it. As night falls over the laboratories of the modern world, physicists still chase the secrets that Planck uncovered more than a century ago. They seek to unite quantum theory with gravity to find the ultimate equation that will describe both the cosmos and the atom. The mystery of light and matter, once confined to a furnace in a Berlin lab, now stretches across the universe itself, from the tiniest particles to the birth of stars. In the end, the story of the early mystery of light and matter is the story of human curiosity. It is the story of how one question, how does heat produce light, led to a revolution that redefined reality. It reminds us that even in the most ordinary phenomena, in the glow of a candle or the warmth of sunlight, lie clues to the deepest truths of existence. And it teaches us that knowledge often begins where certainty ends. The journey of light and matter continues, guided by the same spirit that drove Planck to question the unquestionable. Every photon that shines, every atom that vibrates, carries within it the signature of that moment in 1900 when the universe first revealed its quantum heart. From the silent laboratories of the past to the quantum computers of the future, the legacy of that discovery endures. The mystery that once defied understanding has become the foundation of modern science, a reminder that the universe, no matter how deeply we probe, will always have another secret waiting beyond the light. At the turn of the 20th century, physics stood proud, radiant with confidence. The mechanical universe of Newton, polished by centuries of discovery, appeared complete. Maxwell's majestic equations had woven light and electromagnetism into a seamless tapestry. Thermodynamics had revealed the deep logic of heat and energy. It seemed that nature's last secrets had been tamed and catalogued. The world of science felt as if it were standing atop a mountain, surveying all of creation with perfect clarity. Yet, in that very moment of triumph, a quiet question arose from the shadows, one that would unravel everything humanity thought it knew about the universe. In the heart of Germany, a man named Max Planck was pondering this question. He was not a radical or a rebel. He was, by temperament and philosophy, a conservative, a man who believed in the harmony of natural law and the absolute order of the cosmos. To Planck, the universe was governed by mathematical beauty, by reason and predictability. He did not seek to destroy the old world of physics. He sought only to clarify its final mysteries. But destiny had chosen him to open a door that no one else dared touch, the door to the quantum world. The problem that drew Planck's attention seemed, at first, modest. It was the study of blackbody radiation, the way objects emit light and heat when heated to high temperatures. When an iron rod glows red hot or a furnace radiates white light, it emits a continuous range of electromagnetic waves. Physicists had tried for decades to describe this emission mathematically, to find a formula that matched experimental results. But classical physics stubbornly refused to cooperate. Every theory failed at one end of the spectrum or another. According to the classical laws, the energy radiated at short wavelengths, such as ultraviolet light, should become infinite. This absurd prediction became known as the ultraviolet catastrophe. It was a catastrophe not of nature, but of theory, a sign that something deep within the structure of physics was broken. Planck began his investigation with cautious determination. He approached the problem using the tools of thermodynamics, his area of expertise. He examined how energy was distributed among the oscillators, the hypothetical vibrating charges that emitted radiation inside a heated cavity. He knew that these oscillators must exchange energy with their surroundings, but the pattern of this exchange refused to fit any known rule. As he calculated and recalculated, Planck began to realize that the solution might require abandoning the cherished assumption of continuity. That thought troubled him deeply. For centuries, physics had operated on a single, unshakable belief that energy changes smoothly, that it can be divided into infinitely small portions just as a line can be divided into endless points. This principle was woven into every equation, every theory. To challenge it would mean challenging the very language of physics itself. Yet the data on Planck's desk did not lie. The experimental curve describing blackbody radiation could not be explained by any continuous model. Nature, it seemed, was refusing to play by the rules. One October evening in 1900, after weeks of wrestling with the equations, Planck made a decision that would change science forever. He introduced an idea not out of boldness, but out of desperation. He proposed that the oscillators inside a blackbody could not take on just any amount of energy. Instead, they could only possess discrete amounts, specific packets that were proportional to the frequency of vibration. In mathematical form, this meant that the energy of an oscillator was given by eta of nu, where nu represented the frequency, and h was a new constant, a small, strange number that would soon become one of the cornerstones of physics. It was a breathtaking moment of insight, though Planck himself did not yet grasp its magnitude. He called these packets of energy quanta. The plural, quanta, would become the name of a revolution. By introducing this idea, Planck shattered the notion of continuous energy. He suggested, in effect, that the universe ticks in discrete steps, that energy moves not as a flowing river, but as a stream of individual drops. At first, Planck saw this as a mere mathematical convenience, a tool to make his formula fit the experimental data. But when he compared his equation to the results of Heinrich Rubens and Ferdinand Kuhlbaum, two of the leading experimentalists of the time, the agreement was perfect. The formula matched reality at every wavelength, from the longest to the shortest. Planck had done the impossible. He had solved the blackbody problem. Yet he had also done something more profound. He had cracked open the fabric of reality. When Planck presented his findings to the German Physical Society on December 14, 1900, few in the audience understood their significance. The meeting was quiet, almost routine. There were no gasps of astonishment, no cries of revolution. Planck himself regarded his discovery as provisional, a temporary step toward a deeper understanding that would, he hoped, restore continuity to physics. But history would mark that day as the birth of quantum theory, the day humanity first glimpsed the granularity of nature. What Planck had proposed was nothing less than a redefinition of energy itself. In his model, energy was not an infinitely divisible quantity, but a collection of discrete packets. The amount of energy in each packet was determined by the frequency of vibration multiplied by Planck's constant. This simple equation, eta, encoded a truth so powerful that it would reshape every branch of science. But at the time, its meaning was hidden even from its creator. Planck treated it as a hypothesis, not as a statement about reality. He believed that once a more refined classical theory was developed, the quanta would disappear, replaced by the smooth continuity of traditional physics. Yet the universe does not bend to human expectation. In the years that followed, other scientists began to uncover evidence that supported Planck's strange assumption. The photoelectric effect, where light striking a metal surface ejects electrons, could not be explained by wave theory. Only if light were made of discrete quanta, each carrying energy proportional to its frequency, could the observations make sense. Einstein seized upon this idea, declaring that light itself must be quantized. It was a bold step, one that even Planck initially resisted, but it was the logical extension of his own formula. In that moment, the quanta were no longer mathematical abstractions. They were physical entities. They were the very building blocks of light. Every photon that crossed the void of space carried within it a tiny packet of energy, dictated by Planck's constant. The universe, once thought to be continuous, was now revealed to be digital at its core. The implications rippled outward through every corner of science. If energy came in quanta, then perhaps matter did too. The structure of atoms, long mysterious, began to yield its secrets. When electrons orbit a nucleus, they cannot move in arbitrary paths. They are restricted to discrete energy levels. The colors emitted by glowing gases, the spectral lines observed through prisms, all of these could now be explained as transitions between quantized states. Each line of color was the mark of a quantum jump, a leap of energy that echoed Planck's original discovery. For Planck, this realization was both exhilarating and unsettling. He had not set out to destroy classical physics, but to preserve it. Yet his equation had done the opposite. It had dismantled the very foundations of determinism. It introduced discontinuity, randomness, and limits into a world that once seemed infinite and predictable. Still, Planck's humility and persistence kept him grounded. He viewed science as a dialogue between humanity and nature had spoken in the language of quanta. His revolutionary idea did not come easily. Behind it lay years of intellectual struggle and philosophical conflict. Planck had been raised in a culture of certainty, where science sought absolute truths. He revered the principles of conservation, the belief that energy could neither be created nor destroyed. To accept that energy could exist only in jumps seemed to violate that harmony. Yet Planck trusted the evidence more than his instincts. When the data spoke, he listened. The constant he introduced was minuscule, almost unimaginably small, about 6.626 × 10 gileseconds. To the human scale, it seemed irrelevant, but in the microscopic world of atoms, it ruled everything. It set the scale at which quantum effects become significant, the dividing line between the classical and quantum realms. Without it, there would be no structure in the atom, no stability in matter, no light in the stars. Planck's constant became the heartbeat of the universe, the silent rhythm underlying all creation. As the 20th century unfolded, the world began to catch up with what Planck had unleashed. The quanta inspired a generation of thinkers: Bohr, Heisenberg, Schrödinger, Dirac, each building upon the foundation he had laid. They developed quantum mechanics, a new language of nature that could describe the behavior of electrons, photons, and all subatomic entities. Out of Planck's quiet idea grew the most successful and accurate theory in the history of science. But the journey was far from easy. The quantum world was alien, its laws counterintuitive and often defiant of logic. Particles could behave as waves, waves could behave as particles, and probabilities replaced certainties. The deterministic vision of Newton gave way to the probabilistic reality of Heisenberg. The observer became part of the experiment, and measurement itself seemed to shape reality. These were not ideas Planck would have embraced easily, yet they all traced their origin back to his moment of inspiration in 1900. What began as a modest solution to a thermal problem had become a revolution of thought. Planck had not merely solved an equation, he had revealed a new layer of existence. His quanta were the keys to a hidden kingdom, a microscopic realm where energy danced in discrete steps, where chance governed motion, and where the boundaries between light and matter dissolved. Though Planck himself remained cautious, history would recognize him as the father of quantum physics. His discovery not only explained the mysteries of heat and light, but laid the foundation for technologies that would define the modern world. From lasers and transistors to atomic clocks and quantum computers, every innovation that shapes our civilization today carries within it the echo of Planck's equation. As the sun set on the classical age, a new dawn rose, a quantum dawn, lit by the glow of insight from a man who never sought to change the world, yet did so more profoundly than any of his time. His revolutionary idea of energy quanta redefined not just science, but reality itself. It taught humanity that the universe is not a smooth continuum, but a mosaic of tiny, indivisible moments. A cosmic symphony composed not of flowing melodies, but of single, resonant notes that together form the harmony of existence. In the years that followed his astonishing realization, Max Planck's idea began to ripple outward through the scientific world, touching minds that would soon transform physics beyond recognition. Yet, it was not an easy path. Many of his peers viewed the notion of quantized energy with suspicion. To them, it seemed almost heretical to claim that energy, something so fundamental, could exist only in discrete packets, like coins rather than a continuous flow. Planck himself wrestled with the same discomfort. He had arrived at the concept not out of desire to overturn classical physics, but as a desperate attempt to make the equations fit reality. And yet, as time passed, it became clear that his mathematical trick was far more than that. It was the beginning of a revolution. In laboratories across Europe, scientists began testing and extending Planck's formula. Experimental results spoke louder than theory, and the strange idea of quantization started to show its power. Soon after, a young patent clerk in Bern named Albert Einstein took Planck's constant and used it to solve another mystery, the photoelectric effect. When light struck certain metals, it ejected electrons, but only if the light's frequency was above a specific threshold. No matter how bright the light was, if its frequency was too low, the electrons refused to move. Classical physics had no explanation for this, but Einstein, drawing directly from Planck's quantum hypothesis, proposed that light itself was composed of individual particles, or quanta, of energy, later called photons. This bold step confirmed that the quantum idea was not a mathematical convenience, it was the fabric of reality itself. Planck was astonished by Einstein's audacity. He admired the younger physicist, but found the leap from quantized energy emission to quantized light itself hard to accept. For Planck, the quanta were a property of how energy was absorbed or emitted, not a statement about the nature of light. But Einstein had no such hesitation. He saw that light could behave both as a wave and as a stream of discrete particles, depending on how it was observed. This was the birth of wave-particle duality, a concept that would come to define quantum physics. Planck's modest equation had cracked open the door, and now light itself was walking through it into an entirely new world. As the scientific community debated these shocking ideas, Planck's name grew in stature. He became known as the reluctant revolutionary, the man who had accidentally lit the fuse of modern physics. But for all the fame, he remained humble and cautious. He continued to refine his equations, trying to reconcile his quantum formula with the established laws of thermodynamics and electromagnetism. For him, the universe was a harmonious whole, and any new theory must eventually fit into that grand harmony. What he didn't realize was that the harmony he imagined would never again be the same. The quantum world was not smooth and predictable. It was jumpy, uncertain, and filled with mysteries that defied common sense. By the 1910s, younger physicists were taking Planck's constant and running with it in directions he could scarcely imagine. Niels Bohr used it to construct his model of the atom, showing that electrons orbit the nucleus only in certain fixed energy levels, jumping between them by absorbing or emitting quanta of light. Louis de Broglie later proposed that particles like electrons could also behave as waves, further blurring the line between matter and energy. Werner Heisenberg developed his uncertainty principle, revealing that one could never know both the position and momentum of a particle with absolute precision. And Erwin Schrödinger crafted his wave equation, showing that particles existed as mathematical waves of probability rather than solid points. Every one of these breakthroughs traced its lineage back to that single constant, Planck's constant, the seed from which quantum mechanics grew. It is often said that science progresses one funeral at a time, and in some ways Planck's revolution proved that true. Many older scientists clung to the deterministic worldview of Newton, unwilling to embrace the probabilistic chaos of the quantum realm. Planck himself straddled the two eras. He accepted the success of his own theory, but hoped that one day, someone would find a way to make sense of it within the framework of classical physics. That day never came. Instead, his idea became the foundation for a new physics that left the old one behind. The universe, it seemed, was far stranger, more intricate, and more unpredictable than anyone had imagined. As the decades unfolded, the practical power of Planck's discovery began to show. The quantization of energy explained why atoms were stable, why chemical bonds formed, and why light emitted by different elements came in precise spectral lines. It revealed the inner structure of matter itself, down to the smallest scales. From this understanding arose technologies that reshaped the modern world: lasers, semiconductors, nuclear energy, and quantum computers, all born from the concept of energy quanta. What began as an obscure solution to a thermal radiation problem became the cornerstone of the digital age. In his later years, Planck often reflected on how his discovery had changed the course of science. He once remarked that new truths in physics rarely triumph by convincing their opponents, but rather by the passing of time, as new generations grow up familiar with them. He had witnessed that process firsthand. Young physicists who grew up with his constant in their equations no longer questioned it. They built upon it, extending its reach to realms he had never dreamed of. Though he remained a man of deep philosophical conviction, Planck came to accept that the universe was more mysterious than human reason could fully comprehend. The tragedy of the 20th century also touched his life deeply. World wars ravaged Europe, and Planck, ever the moral and intellectual pillar of German science, faced immense personal loss. Yet even in those dark times, he continued to advocate for the purity of science and the search for truth. His belief in the harmony of nature remained unbroken. He saw quantum theory not as a disruption of order, but as an unveiling of a deeper, subtler order, one that operated beyond the limits of classical logic. In the grand story of discovery, Planck's contribution stands as a turning point, a moment when humanity first glimpsed the hidden fabric of reality. His revolutionary idea of energy quanta marked the birth of a new kind of physics, one that defied the intuition of centuries. It opened the door to a microscopic universe where particles danced in probabilities and waves, where certainty dissolved into possibility, and where the act of observation itself could change what was being observed. Looking back, it is clear that Max Planck did more than propose a new constant or a new formula. He transformed the way we think about nature. His discovery taught us that the universe is not a simple machine, but a symphony of discrete notes, each one a quantum of energy, each one contributing to the cosmic melody. From the glow of a star to the spark of a computer chip, his constant is there, quietly governing the rhythm of the universe. And though Planck himself may have hesitated to accept the full implications of his theory, his courage to follow truth, wherever it led, stands as one of the greatest acts of scientific faith. He proved that even the smallest step, a new equation, a tiny constant, can open doors to realities beyond imagination. The revolution he started continues today, as physicists probe deeper into the quantum world, chasing the same light that first illuminated Planck's mind more than a century ago. In that light lies the essence of his genius, not in seeking revolution, but in his devotion to understanding nature as it truly is. From the heat of glowing matter to the mysteries of the cosmos, his discovery endures, whispering a timeless truth, that in the smallest quanta of energy, the universe reveals its grandest secrets. At the dawn of the 20th century, the world of physics stood proudly on the achievements of centuries past. From the celestial mechanics of Newton to the elegant equations of Maxwell, science had woven a tapestry of order and predictability that seemed to describe the entire universe. Every motion, every beam of light, every falling apple was thought to obey the unbreakable laws of classical mechanics. The universe appeared as a grand machine, operating in perfect harmony under immutable rules. But in the quiet corridors of German laboratories, an unassuming professor named Max Planck was about to challenge that certainty. In the year 1900, without knowing it, he would give birth to a new kind of science, the quantum theory, and with it, a new vision of reality itself. The story began with a mystery that seemed almost trivial: how objects radiate heat. When a piece of metal glows red, hot, or the sun shines in the sky, they emit light of different colors depending on their temperature. Physicists had long tried to calculate how much energy was radiated at each color or wavelength. Yet the equations refused to cooperate. The prevailing classical theories, rooted in Maxwell's electromagnetic laws, predicted that as an object grew hotter, it should emit infinite energy at high frequencies, a disaster known as the ultraviolet catastrophe. But nature did not behave that way. The experiments showed a clear pattern. The energy rose with frequency to a peak, then declined. It was a puzzle that defied the established principles of physics. Planck, a man of deep intellect and disciplined thought, was not looking to overturn the laws of nature. He was a conservative physicist by temperament, devoted to finding harmony in the equations that governed reality. Yet, as he studied the problem of blackbody radiation, he realized that the traditional approaches all failed. He tried every classical trick, adjusting constants, reshaping formulas, but the experimental data would not yield. Desperate for a solution, he took a step that went against every instinct of the physicist he was. He proposed that energy was not emitted continuously but in discrete packets, quanta. It was not a belief, but a mathematical necessity. Planck introduced the idea as a last resort, a way to make the numbers fit the observations. He wrote an equation that assumed the energy of each light wave depended on its frequency multiplied by a tiny constant, a constant so small it almost seemed insignificant. That constant, now known as Planck's constant, became the foundation stone of quantum theory. It represented the smallest possible unit of energy, the grain from which the universe's continuous waves of light and heat were built. When Planck compared his theoretical predictions with the experimental data, the match was perfect. His equation described nature's behavior flawlessly. The catastrophe vanished, replaced by a beautifully consistent curve. In that moment, Planck had unknowingly crossed the threshold into a new world. The year was 1900, and the quantum age had begun. Yet Planck himself did not fully understand the revolution he had unleashed. He regarded his idea as a mere mathematical trick, a temporary fix until a more conventional explanation could be found. He could not imagine that the very continuity of nature, the smooth flow of energy and motion that classical physics revered, had been broken at the deepest level. But others would soon see what he had done. His constant implied that energy, light, and even matter might be quantized, existing in indivisible chunks rather than flowing endlessly. The implications were staggering. In Berlin, as Planck presented his results to the German Physical Society, the audience listened politely, unaware that they were witnessing the birth of a new epoch. His presentation was modest, almost apologetic. There was no triumphant declaration, no sense of revolution. The equations were clear, the data undeniable, but the meaning remained hidden beneath the calm surface of his words. Yet in the shadows of that lecture hall, the future of physics had already changed forever. The scientific community at first treated Planck's hypothesis as a curiosity. The idea of quantized energy seemed absurd. For centuries, scientists had been taught that all physical processes were continuous, that motion, heat, and light flowed smoothly through space and time. The notion of energy jumping from one discrete level to another defied both logic and experience. But nature, as it turned out, had its own logic, far stranger than anyone suspected. In the years that followed, the seeds Planck planted began to take root in minds more daring than his own. Albert Einstein, still a young man working in a Swiss patent office, would soon take Planck's constant and breathe life into it. In 1905, he used the concept to explain the photoelectric effect, how light could knock electrons loose from metal surfaces. Classical physics could not explain why only certain frequencies of light could free the electrons, regardless of the light's brightness. But Einstein realized that if light came in quanta, or photons, each carrying an energy proportional to its frequency, the mystery disappeared. It was the first direct evidence that Planck's quanta were real physical entities, not mere mathematical devices. For this discovery, Einstein would later receive the Nobel Prize, though he always credited Planck as the true originator of the quantum idea. Meanwhile, other scientists began to explore the strange consequences of quantization. The old certainties of Newtonian mechanics were slowly dissolving. The quantum concept explained why atoms emitted light at specific colors, why matter remained stable, and why the universe did not collapse into chaos. Yet each answer raised new questions. How could energy come in lumps? How could light be both wave and particle? How could the laws of physics change at the smallest scales of existence? The classical world had no vocabulary for such mysteries. Planck watched these developments with cautious fascination. He admired Einstein's courage, but could not bring himself to believe that light itself was quantized. He still hoped his own theory would one day be absorbed into the classical framework. He did not realize that he had already torn open a crack in that framework that could never be closed. Through that crack, the future was pouring in. The turn of the century was a time of breathtaking transformation. Steam engines and telegraphs were giving way to electricity and radio waves. The industrial world thrived on the power of applied physics, while deep beneath its surface, a revolution was quietly unfolding in the laboratories of Europe. In universities from Berlin to Cambridge, young physicists began to suspect that the old world of certainty was an illusion. The universe was not a clockwork machine, but a vast ocean of probabilities, vibrations, and quanta. Planck's equation had revealed the hidden rhythm of that ocean. The birth of quantum theory in 1900 was not marked by explosions or proclamations. It was a whisper, a gentle shift in the mathematics of radiation. But from that whisper grew the loudest revolution in science's history. Theories of relativity, atomic structure, and nuclear energy all found their roots in Planck's insight. His constant h became the key to the subatomic world, defining the scale at which quantum effects dominate and classical intuition fails. By the time Planck fully grasped the depth of his discovery, physics had already entered a new era. Niels Bohr used the quantum concept to build his model of the atom, explaining how electrons could orbit the nucleus in fixed energy levels, emitting light only when they jumped between these levels. Werner Heisenberg and Erwin Schrödinger would later transform Planck's quanta into the formal language of quantum mechanics, where probability replaced certainty and observation itself became part of reality. But all of that began with Planck's single step, the idea that energy is not continuous. For the world at large, the implications of this moment were invisible. Outside the quiet world of academia, people continued their lives unaware that the very fabric of their reality had been redefined. The discovery would take decades to filter into the public imagination. Yet every modern technology, from computers and lasers to GPS and medical imaging, traces its lineage to that fateful year when a solitary German physicist defied tradition and followed truth into the unknown. It is almost poetic that Max Planck, a man seeking order, became the father of uncertainty. His quantum theory did not merely solve a problem. It revealed that nature's simplicity lay in its smallest divisions. Beneath the smooth flow of energy and motion, reality shimmered with discontinuity. Tiny steps, discrete levels, and sudden leaps. It was a new kind of beauty, one that defied human expectation but captured the rhythm of the cosmos. The birth of quantum theory was, in a sense, the birth of the modern world. It marked humanity's first glimpse into the microscopic universe, a place where the rules of everyday life no longer applied. It shattered the illusion of certainty and replaced it with a deeper, more mysterious truth that the universe, at its core, is built not on continuity but on quanta, finite packets of possibility. The year 1900 stands as a quiet monument in the history of science. There were no headlines, no celebrations, no grand discoveries shouted from rooftops. Only a man, a blackboard, and an equation that fit the data. But that equation was a doorway. Behind it lay the future, a world of strange particles, uncertain realities, and boundless potential. And though Max Planck could not have imagined it then, his reluctant leap into the unknown had forever changed what it means to understand nature. It was not the end of the old physics, but the beginning of something far greater. The moment when humanity first peered into the invisible machinery of existence and saw, for the first time, the quanta that make up everything. As the first years of the 20th century unfolded, the quiet storm that Max Planck had set in motion began to gather strength. The idea of quantized energy, at first treated as a mathematical curiosity, started to reveal its power in unexpected ways. Across Europe, young physicists began to pick up the threads of Planck's discovery and weave them into a new vision of reality. The classical order, so long seen as absolute, was beginning to tremble. Nature itself seemed to whisper a new language, one of probabilities, vibrations, and discontinuities. And at the center of it all stood Planck's constant, that tiny number that divided the old universe from the new. The story of the birth of quantum theory was not one of instant triumph. It was a slow awakening, a battle of ideas fought not on battlefields but in lecture halls, journals, and the silent thoughts of men who dared to imagine what others dismissed as impossible. Planck's hypothesis had solved the problem of blackbody radiation, but no one, not even Planck, understood what it truly meant. Was energy really emitted in indivisible packets? Could the universe itself be quantized? Such questions hung over the scientific world like unspoken riddles. Then, in 1905, Einstein's paper on the photoelectric effect arrived like a flash of lightning. By extending Planck's idea beyond its original purpose, Einstein made a radical claim: light itself must consist of discrete quanta of energy. He proposed that these light quanta could knock electrons loose from metal surfaces, and that the energy of each quantum depended solely on its frequency. It was a direct challenge to the wave theory of light, which had been triumphantly confirmed by the experiments of the 19th century. Now Einstein was saying that light could act not only as a wave, but as a stream of particles, photons. The implications were staggering. Planck's constant, once an obscure symbol in an equation about thermal radiation, had suddenly become the key to understanding the dual nature of light. Planck was both astonished and uneasy. He admired Einstein's courage, but struggled to accept the physical reality of light quanta. For him, quantization was a mathematical trick, not a statement about the nature of reality. Yet reality itself refused to conform to comfort. Einstein's theory was confirmed by experiment after experiment. The world was changing and physics was following it into the unknown. By 1913, Niels Bohr built upon Planck's and Einstein's work to construct a new model of the atom. In his vision, electrons orbited the nucleus in discrete energy levels, jumping between them by absorbing or emitting quanta of light. The colors of the hydrogen spectrum, once a mystery, now fell neatly into place. It was a triumph of the quantum idea. And yet, the mystery deepened. Why should electrons behave this way? Why did they not spiral into the nucleus, as classical physics predicted? The answers lay buried in the mathematics that would soon give birth to quantum mechanics. Planck, ever the scholar, watched this transformation with quiet pride and cautious skepticism. He was delighted that his discovery had inspired such progress, yet he could not fully embrace the radical conclusions drawn from it. For a man who had spent his life believing in the order and continuity of nature, the notion that the universe functioned through discrete leaps felt almost philosophical heresy. But the evidence was undeniable. One by one, the great minds of the new century, Einstein, Bohr, Heisenberg, Schrödinger, and Dirac, expanded on Planck's foundation, building a new physics that would rewrite humanity's understanding of existence. In 1918, Max Planck was awarded the Nobel Prize in Physics for his discovery of energy quanta. It was official recognition of his role as the father of quantum theory. Yet in his acceptance speech, he remained characteristically humble. He did not claim to have invented a new science or destroyed an old one. Instead, he spoke of the physicist's duty to seek truth wherever it leads, even when that truth challenges the deepest assumptions. His words reflected the inner conflict of a man who had opened a door to a world he did not fully wish to enter. Beyond the walls of academia, the wider world was in turmoil. The First World War had shaken Europe to its core, and the rise of new technologies, radio, X-rays, and electricity, hinted at the growing power of scientific discovery. Unbeknownst to most, many of these technologies relied on principles rooted in quantum theory. The rules that governed atoms were no longer philosophical curiosities, they were becoming the foundation of a new technological civilization. The light bulbs that illuminated the night, the radios that carried voices across continents, the nascent electronic devices, all drew from the strange, silent mathematics that Planck had unleashed in 1900. Yet even as quantum theory gained ground, it refused to offer comfort. It was not a simple replacement for classical physics, but a transformation that demanded a new way of thinking. In the quantum world, certainty gave way to probability, determinism to chance. Electrons could exist in multiple places at once, particles behaved like waves, observation itself altered reality. It was as though the universe had been unmasked, revealing not the clockwork of Newton, but a shimmering web of potentialities, and all of it could be traced back to that single insight in Planck's study, the idea that energy comes in quanta. By the 1920s, the quantum revolution had become unstoppable. Heisenberg's matrix mechanics, Schrödinger's wave equation, and Dirac's unification of relativity and quantum theory painted a picture of nature that was both terrifying and beautiful. Planck's constant appeared in every equation, a quiet reminder of the moment when the old world had cracked open. The year 1900 was no longer just a date, it was the line dividing two eras of science. Before it lay the universe of certainty. After it, the universe of quanta. Planck lived to see his discovery transform the world. In his later years, he reflected on how his work had changed not only physics but philosophy itself. He once said that science advances not because old theories are refuted, but because new generations grow up familiar with the new ideas. He had watched that process unfold with his own eyes. The young physicists of the 1920s, bold, imaginative, unafraid, accepted the quantum world as a fact of life. They no longer questioned whether energy could be quantized, they sought instead to understand its deeper meaning. Meanwhile, the practical applications of quantum theory began to reshape society. The invention of the transistor, the development of lasers, the birth of nuclear energy, all were rooted in the principles Planck had discovered. What began as an abstract formula to describe the glow of heated matter had become the backbone of modern civilization. Every computer chip, every digital signal, every atomic clock bears the silent imprint of that first quantum leap. As his fame grew, Planck became a symbol of intellectual integrity in turbulent times. Through the chaos of war and political upheaval, he remained steadfast in his devotion to truth and knowledge. He endured personal tragedy, the loss of his sons in war, the destruction of his home, the persecution of colleagues. Yet he never lost faith in the human spirit or in the order of nature. He believed that beneath the apparent chaos of the quantum world lay a deeper harmony, one that reflected the unity of creation itself. In the final years of his life, Planck often spoke of the wonder of discovery. He had not sought revolution, yet he had changed the course of science forever. He saw himself not as a destroyer of old laws, but as a bridge between two worlds, the world of continuity and the world of quanta. Through that bridge, generations of physicists would cross, exploring realms he could only imagine. The birth of quantum theory in 1900 stands today as one of the most profound moments in human history. It was the moment when humanity's understanding of nature took a leap beyond the visible, into the invisible realm of atoms and energy. From that moment onward, the boundaries between matter and light, particle and wave, certainty and chance, began to blur. The old universe, once seen as a predictable mechanism, revealed itself to be something far more intricate, a dance of quanta, a symphony of possibilities. And though Planck himself remained a reluctant revolutionary, history remembers him as the man who opened the first door to the quantum world. Through that door came the greatest minds of the 20th century, carrying with them the torch of discovery that would illuminate everything from the atom to the stars. The spark he struck in 1900 still burns today, in every experiment, in every theory, in every mystery yet to be unraveled. It is a light that never fades, a reminder that even the smallest constant can reshape the cosmos. In the glow of that light, we see the true legacy of Max Planck, the moment when the human mind, reaching for understanding, touched the very fabric of reality, and found it made of quanta. The challenge to classical physics marked one of the most dramatic turning points in the history of science. For centuries, classical physics had been the unshakable foundation upon which humanity built its understanding of the universe. It was a world governed by certainty, by the predictable laws of Newton and Maxwell, where every motion, every force, and every beam of light could, in principle, be calculated with absolute precision. The universe was a vast, elegant machine, and given enough knowledge, one could predict its every move. But when the 20th century dawned, that perfect machine began to show cracks. In the flicker of light, in the heat of glowing matter, in the strange behavior of electrons, the old rules began to break. The elegant equations that had once described everything began to fail when peering into the world of the very small. It was here that the discoveries of Max Planck began to shake the foundations of classical thought. His idea that energy could exist only in discrete packets, quanta, was not just a mathematical adjustment, it was an earthquake that trembled through the core of physics. The classical vision of smooth, continuous energy was gone. Suddenly, nature appeared to take tiny, distinct steps rather than flowing in a seamless stream. This was not merely a correction to the equations, it was a fundamental change in the way reality itself was understood. Yet, many scientists resisted. For them, classical physics was not just a theory, it was the truth of the universe. The thought that energy, light, or matter could behave in such strange, discontinuous ways seemed absurd. The challenge grew deeper as new discoveries piled upon one another. Einstein's explanation of the photoelectric effect revealed that light behaved as both a wave and a particle. Bohr's atomic model showed that electrons could occupy only specific energy levels, leaping from one orbit to another without ever existing in between. Heisenberg's uncertainty principle shattered the dream of perfect measurement, proving that one could never know both a particle's position and momentum with absolute accuracy. Schrödinger's wave mechanics painted a picture of a universe made not of definite objects, but of probabilities and possibilities. Each of these breakthroughs struck another blow to classical physics, tearing away its comforting predictability. The universe, once thought to be a grand clockwork of certainty, now seemed filled with randomness and mystery. For many, this new view of nature was deeply unsettling. Classical physics had promised control, order, and understanding, a world in which every effect had a clear cause. But the quantum world defied such logic. Particles appeared to behave differently when observed. Matter could exist in multiple states at once. Even the act of measurement could alter reality. It was a realm that seemed to mock human intuition. Yet, despite its strangeness, the new physics worked. Its equations predicted experimental results with astonishing precision. The more scientists explored the microscopic world, the clearer it became that classical laws were only approximations, a grand but limited description of a much deeper and stranger truth. The challenge to classical physics was not merely scientific, it was philosophical. It forced humanity to confront uncomfortable questions about the nature of reality. Was the universe truly deterministic, unfolding like a clock according to fixed laws? Or was it fundamentally uncertain, its outcomes governed by chance? Could human beings ever truly know the world, or were we forever limited by the boundaries of our perception? These were not questions that Newton or Maxwell could answer. They belonged to a new era, one defined by doubt and discovery in equal measure. As the 20th century advanced, the quantum theory proved itself again and again, not only in experiments but in practical technology. The very foundations of the modern world, computers, lasers, nuclear energy, and even the devices used to study the stars, were built upon the laws that had once seemed so alien. The challenge to classical physics had not destroyed the old order, it had expanded it, revealing that the universe was more complex, more dynamic, and more wondrous than anyone had dared to imagine. The story of this challenge is not just the story of equations or experiments, it is the story of a transformation in human thought. It is about the courage to question what seemed unquestionable, to accept that certainty might be an illusion, and to embrace the unknown as the path to truth. From Planck's quanta to Einstein's photons, from Bohr's atoms to Schrödinger's waves, each discovery pushed humanity further into this new territory. The classical world of predictability had given way to a quantum world of possibilities. In the end, the challenge to classical physics was not a defeat, but a rebirth. It reminded humanity that science is not the pursuit of comfort, but of truth. And that truth often lies beyond the limits of imagination. The old world of cause and effect had shattered, revealing beneath it a universe alive with uncertainty, rhythm, and mystery. And in that new understanding, physics found not chaos, but a deeper harmony, one that continues to shape the way we see existence itself. The rise of Albert Einstein marked a turning point, not only in physics, but in the very way humanity perceived reality. When Max Planck introduced his concept of energy quanta in 1900, it was a spark, a strange, radical idea that energy might not flow smoothly, but instead come in small, indivisible packets. Yet, it was Einstein who transformed that spark into a blazing revolution. He took Planck's hesitant hypothesis and gave it a profound, physical meaning. To Einstein, the idea of quantization was not just a mathematical trick, it was a window into the deep and mysterious nature of light itself. In 1905, in what would later be called his miracle year, Einstein published a paper that forever changed the course of science. He proposed that light, the very essence of vision and warmth, could behave not as a continuous wave, but as a stream of discrete energy packets called photons. This bold assertion explained the puzzling photoelectric effect, a phenomenon in which light striking a metal surface could eject electrons. Classical physics had failed to describe it correctly, predicting that the brightness of light, not its frequency, should determine the energy of the ejected electrons. Yet experiments showed the opposite. Einstein realized that only by accepting light as quantized could the mystery be solved. The energy of each photon, he said, depended on its frequency, not its brightness. At first, few believed him. The concept was too strange, too revolutionary. For centuries, light had been understood as a wave, a smooth oscillation in the fabric of the electromagnetic field. To suddenly claim that it could also act as a particle, a discrete bundle of energy, seemed to shatter everything physicists had known. Even Planck himself was uneasy with Einstein's interpretation, hesitant to extend quantization beyond the abstract world of equations. But Einstein's courage lay in his willingness to confront contradiction, to embrace paradox. He was guided not by tradition, but by the simple, unwavering demand that theory must match observation. His insight went far beyond the photoelectric effect. It hinted at a new and deeper duality, that light, and perhaps all matter, could exist in two forms at once, as both wave and particle. This idea would later form the foundation of quantum mechanics, but in Einstein's time, it was a revelation. He had opened a door to a world where the familiar boundaries of physics no longer applied. The universe, once seen as a mechanical system governed by absolute laws, now seemed to dance to a rhythm both predictable and mysterious. Einstein's work did not stop there. In the following years, he used quantum principles to explain the behavior of gases, the motion of atoms, and even the delicate fluctuations in energy that occur in seemingly empty space. Yet, what made Einstein truly remarkable was not only his genius for equations but his imagination. His ability to see beyond the visible, to question the very foundations of knowledge. For him, science was not just about numbers, it was a journey into the unknown, a search for unity beneath the apparent chaos of nature. The world eventually recognized the power of his ideas. In 1921, Einstein was awarded the Nobel Prize in Physics, not for his theory of relativity, as many assume, but for his explanation of the photoelectric effect. It was a recognition that his quantum insight had laid the groundwork for a new era of physics. This moment marked the true beginning of the quantum age, the dawn of a scientific revolution that would reshape everything from the atom to the cosmos. But Einstein himself remained ambivalent about where quantum theory was headed. As the new generation of physicists, Bohr, Heisenberg, Schrödinger, expanded upon his ideas, they introduced concepts that disturbed him deeply: uncertainty, probability, and the idea that observation could influence reality itself. Einstein's mind, rooted in a belief in order and determinism, could not fully accept a universe governed by chance. God does not play dice with the universe, he famously declared. Yet, in a beautiful irony, it was his own discoveries that had made such a universe possible. Despite his discomfort, Einstein's contributions became the cornerstone upon which modern quantum physics was built. His vision of quantized light led to the understanding of the photon, which today powers lasers, solar cells, and fiber optic communication technologies that define the modern world. His equations continue to guide the exploration of the smallest particles and the farthest galaxies. In the grand story of science, Einstein's role was that of the visionary who saw further than anyone before him, the genius who dared to redefine the meaning of light. He bridged the gap between the classical and quantum worlds, standing at the threshold of two realities. The door he opened has never closed. Through it, humanity continues to peer into the heart of nature, seeking answers to questions that still defy imagination. Einstein's legacy is not only in his discoveries but in his spirit, the courage to challenge the impossible and to believe that even the most ordinary phenomena, like a beam of light, can hold the key to the universe's deepest secrets. The rise of quantum mechanics in the 1920s marked one of the greatest intellectual revolutions in human history. The world of science had reached a point where the rules of classical physics no longer worked. The behavior of atoms, electrons, and light defied every established law. Out of this confusion emerged a new generation of thinkers: Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, each contributing a piece to the great puzzle of the quantum world. What they built was not merely a theory, but a new way of seeing reality itself, one that would forever alter humanity's understanding of nature. It began with Niels Bohr, the quiet yet deeply philosophical Danish physicist who believed that the atom was not just a mechanical structure, but a realm of mystery. Building upon Planck's quanta and Einstein's photons, Bohr proposed his atomic model in 1913. In it, electrons did not orbit the nucleus in random paths, as once imagined, but occupied specific, quantized energy levels. When these electrons jumped between levels, they emitted or absorbed precise amounts of energy. This bold idea explained the spectral lines of hydrogen, those beautiful patterns of light that no classical theory could decipher. Bohr's model brought order to chaos, yet it also revealed that nature behaved in discrete steps, not smooth continuities. The atom, once thought to be a miniature solar system, now appeared to follow rules unlike anything in the macroscopic world. But Bohr's model was only the beginning. As experiments grew more precise, scientists discovered that even this new picture could not fully explain the behavior of particles at the smallest scales. Into this mystery stepped a young German physicist named Werner Heisenberg. In 1925, Heisenberg introduced matrix mechanics, a radical mathematical framework that abandoned the idea of definite orbits entirely. To him, what could be known were not the paths of electrons, but the probabilities of their behaviors. In his view, physics was not about describing where things are, but about predicting the outcomes of measurements. This led him to one of the most profound discoveries in all of science: the uncertainty principle. Heisenberg's principle declared that the more precisely one knows a particle's position, the less precisely one can know its momentum, and vice versa. This was not a flaw in human measurement, but a fundamental feature of nature. The universe itself was woven with uncertainty. This revelation shattered the old dream of total predictability. The clockwork universe of Newton was gone, replaced by a dynamic, probabilistic one. The very act of observing, Heisenberg showed, influenced what was being observed. Reality was not a fixed stage, but an unfolding process, deeply connected to the observer. Meanwhile, another visionary, Erwin Schrödinger, offered a different yet complementary view. In 1926, he developed wave mechanics, a mathematical description in which particles like electrons were represented not as tiny dots, but as waves spread out through space. These waves, he proposed, did not describe the path of a particle, but the probability of finding it in a certain region. Schrödinger's famous equation became one of the most important tools in all of physics, capable of describing the structure of atoms and molecules with astonishing precision. Yet, it came with philosophical paradoxes. If an electron could exist in multiple states at once, what did that say about reality? Was the world itself a grand superposition of possibilities waiting to be observed? This question led to the now famous thought experiment of Schrödinger's cat, a paradox meant to expose the strangeness of quantum theory. In this scenario, a cat sealed in a box could be both alive and dead at the same time until observed. It was an absurd image, yet it captured the unsettling implications of quantum mechanics. The line between possibility and reality had blurred. The universe seemed to exist in a state of potential, collapsing into definite form only when measured or observed. Through the works of Bohr, Heisenberg, and Schrödinger, quantum mechanics evolved into a complete framework. Bohr's Copenhagen interpretation suggested that the act of measurement itself brings reality into being, that before observation, particles exist only as probabilities. This idea, though deeply controversial, became one of the cornerstones of modern physics. It challenged not only scientific assumptions but philosophical beliefs about objectivity, determinism, and the nature of truth. Despite its mysteries, quantum mechanics quickly proved its power. Its predictions matched experiments with stunning accuracy. It explained the structure of atoms, the nature of chemical bonds, the behavior of light and matter, and even the properties of solids and semiconductors. The theory did not merely describe the world, it reshaped it. Technologies such as transistors, lasers, and nuclear energy emerged directly from its principles, transforming modern civilization. Yet, the philosophical debate never ended. Einstein himself, though the father of the quantum idea, could not accept its indeterminacy. He famously argued with Bohr, insisting that God does not play dice. Bohr replied, "It is not for us to tell God how to run the universe." Their debates defined an era, symbolizing the tension between human intuition and the strange logic of the quantum realm. In the end, the birth of quantum mechanics was more than a scientific triumph. It was a revolution in human thought. It revealed that reality is far stranger, more subtle, and more interconnected than anyone had ever imagined. The work of Bohr, Heisenberg, and Schrödinger opened a door into a world of probabilities and paradoxes, where certainty dissolved and mystery reigned. And yet, in that uncertainty lay the deepest beauty of all, a glimpse into the hidden rhythm of the cosmos, where matter and energy dance in patterns of endless possibility. The legacy of quantum theory stands as one of humanity's greatest intellectual achievements. A revolution that changed not only physics, but the entire way we perceive reality. From the trembling beginnings of Max Planck's discovery to the bold insights of Einstein, Bohr, Heisenberg, and Schrödinger, the quantum revolution unfolded as a story of courage, imagination, and mystery. It revealed a universe far beyond the grasp of common sense, a world that is unpredictable, probabilistic, and yet astonishingly precise in its mathematical order. The 20th century witnessed the birth of this new physics, and the 21st continues to live in its shadow and brilliance. The strange, invisible world of quantum mechanics became the foundation of modern civilization, powering every piece of technology that defines human progress. The story of quantum physics did not end with its discovery, it was only the beginning. The principles born from the minds of those early pioneers began to shape the technologies that would transform life itself. The transistor, the heart of every computer chip, was built upon the understanding of quantum behavior in semiconductors. Without quantum mechanics, there would be no computers, no smartphones, no internet. The lasers that read DVDs, perform eye surgeries, and drive modern communication are direct products of quantum ideas. The MRI scanners that peer into the human body, the GPS satellites that navigate our world, and even the atomic clocks that measure time with unimaginable accuracy all owe their existence to the strange laws discovered in the early 20th century. Yet, the most remarkable impact of quantum theory lies not only in technology, but in the way it reshaped human thought. It shattered the belief that the universe was a machine operating by simple, deterministic rules. It showed that reality itself is layered, that beneath the visible world of certainty lies a deeper, more mysterious realm where probabilities rule. Particles can exist in multiple states, light can behave as both wave and particle, and observation itself can alter the outcome of an event. This was not just science, it was philosophy written in the language of mathematics. Quantum mechanics also brought forth one of the most mind-bending concepts in all of science: entanglement. When two particles become entangled, they remain connected no matter how far apart they are. A change in one instantly affects the other, defying the limitations of space and time. Einstein called it spooky action at a distance, unable to accept it fully, yet decades later, experiments proved it true. This strange phenomenon hinted at a deeper unity in nature, that everything in the universe might be connected in ways we cannot yet fully understand. As the decades passed, scientists learned not only to describe these quantum effects but to harness them. Today, a new revolution is underway: the rise of quantum technology. Quantum computers, unlike classical ones, do not process information in bits of ones and zeros, but in quantum bits, or qubits, which can exist in multiple states at once. This allows them to perform calculations far beyond the reach of traditional machines. With them, humanity may one day simulate molecules for new medicines, solve unsolvable equations, and even unlock the secrets of artificial intelligence. Quantum communication promises unbreakable security through the laws of physics themselves, and quantum sensors are redefining how precisely we can measure the universe. But quantum theory is not only about power, it is also about humility. It reminds humanity of the limits of knowledge. It teaches that certainty is an illusion and that truth is often hidden beneath layers of mystery. Even today, physicists debate what quantum mechanics truly means. Does the wave function represent reality itself, or merely our knowledge of it? Does the universe split into many worlds with every quantum decision, as some interpretations suggest? Or does reality exist only when observed? The answers remain elusive, but the questions themselves reveal the beauty of human curiosity, the drive to seek understanding even when the answers defy imagination. The influence of quantum mechanics reaches beyond science into art, philosophy, and spirituality. It has inspired poets and thinkers to reimagine existence as a dance between possibility and perception, where every act of observation becomes a creative act. The boundaries between the observer and the observed blur, echoing ancient philosophical ideas that consciousness and reality may be intertwined. What began as an effort to explain the glow of heated metal ended as a revolution in the human conception of existence. Looking back, the legacy of quantum theory is not just a list of discoveries or inventions. It is the story of a transformation, of how humanity dared to look into the invisible and found a universe more wondrous than anyone could have dreamed. It is the story of minds that refused to stop at the surface, who questioned the unquestionable, and who rewrote the laws of nature itself. From Planck's cautious first steps to the dazzling breakthroughs of modern quantum science, this journey has carried us from the visible world into the invisible heart of reality. Today, we live surrounded by the fruits of that revolution. Every screen we touch, every digital signal we send, every beam of light that carries our voices across the planet, all are echoes of the quantum world. And yet, even with all our progress, we stand only at the beginning. The mysteries of quantum reality are far from solved. They stretch out before us, vast and humbling, inviting the next generation to explore. The genius who opened the door to quantum physics set humanity on a path that may never end, a path toward understanding not only the universe but ourselves. In the trembling heart of the atom, in the flicker of a photon, in the uncertainty that governs all things, lies the story of our quest for knowledge, a story that continues to unfold one quantum leap at a time.